Hello everyone. So we're just taking a look at the idea of an enthalpy changes and taking a look at enthalpy of reactions and molar enthalpies. Essentially what this comes down to is how do we measure heat or heat energy. We use the term enthalpy to indicate both the potential and kinetic energy that is occurring. So enthalpy can be both the potential energy in chemical bonds as well as the kinetic energy found in the temperature or the motion of those bonds. And so just as an example here, we take a look at a reaction where we have zinc reacting with hydrochloric acid, and it is going to form hydrogen gas and zinc chloride. Now, the chemical bonds within here are losing energy, right? That chemical energy is moving somewhere. And what we have here is that energy is then being picked up by the surroundings. In this case, it's probably a calorimeter because the diagram is suggesting water. So that is enthalpy. Molar enthalpy would just be indicating how much energy, right? So this would tell you the total decrease, the total enthalpy. This will be the total enthalpy increase. And notice energy is not created or destroyed. It's just maintaining here. But if we talked about molar enthalpy, what we would be talking about, molar enthalpy, is just how much energy per mole of a substance. For example, if I said, well, this is a reaction, how much energy would be released per mole of zinc or per mole of hydrochloric acid? How much, given this much is reacting, how much actual energy is going to be released? Now, there are several ways that we can mark this, but usually we're using something called a delta H notation. That delta H is going to represent basically an enthalpy change. In this spot right here, we're going to say what is happening. Now, this could be a dilution or solution, meaning it is dissolving. The substance is decomposing or forming, combusting, or just anything that's specified reaction. So R is kind of just a generic term. If we put an M after this, right here, put an M here, this would be simply saying per mole of that substance. And just to help take a look at what's actually happening, we would put the type of substance here. So we put the substance underneath, and so you'd have the, let's say, for example, if you had delta CHM of CH4, this would be saying how much energy, this would be the, how much enthalpy per mole of methane when methane is combusting. What is happening? And then we would be assigning a value to this. So ultimately what this comes down to is a formula that we can use. Q is equal to NH, and really what this is just saying is Q, or the enthalpy, is equal to the number of moles multiplied by the molar enthalpy of reaction. Okay, So let's take a look at a couple of examples here. Okay, differentiate between enthalpy change and molar enthalpy. So again, enthalpy change is simply us saying how much energy per mole of substance. Okay, how much energy per mole. Yeah. Okay, so let's take a look at a few examples here. The first one here, differentiate between enthalpy change and molar enthalpy. This would be just simply the total energy transferred, where this will get you the amount of energy per mole of a substance, right? So this is not talking about the total of what's happening, but that would be per mole. So if you had less than a mole reacting, obviously the total amount of energy would be less than the molar enthalpy. If you had more than 1 mole of a substance reacting, the total enthalpy change would be more than the molar enthalpy. This is just how much on a per mole basis. If we take a look, if we've got a case here where we've got 50 milliliters of a 1 mole per liter hydrochloric acid and neutralized by 75 milliliters of 0.75 mole per liter sodium hydroxide, the temperature of the resulting changes goes from 20.2 to 25.6 degrees Celsius. The enthalpy change in this entire reaction, okay, we can figure that out using Q is equal to mc delta T. That total amount of energy, that enthalpy, is going to be equal to the mass. Now, given we've got 125 milliliters, means 125 grams, multiplied by the heat capacity of water, 4.19 joules per gram degrees Celsius. And the change in temperature is 5.4 degrees Celsius. So that total amount of enthalpy change, when you multiply those all together, is 2,828.25 joules, or we could simply say that this is 2.83 kilojoules of energy. Now, if we want to determine the hydrochloric acid molar enthalpy, well, we know how much change has happened. What we're really looking for is H, given the total amount of energy that has been transferred. And we're going to simply divide it by the number of moles of hydrochloric acid to get the amount of energy per mole of hydrochloric acid. Another way of us looking at that is Q over N is equal to H. The amount of energy is 2.83 kilojoules. And we're going to divide that by the number of moles. The number of moles of hydrochloric acid is equal to the concentration times the volume. And given the fact it's a 1 mole per liter, 50 milliliters will get you 50 millimoles, or 0.05 moles. 0.05 moles. And running through this calculation, 2.83 divided by 0.05 moles means that the rate of reaction is 56.6 kilojoules per mole of hydrochloric acid. Now, we did not have 1 mole of hydrochloric acid, which is why we did not get a full 56.6. We only had this little 0.05 moles of it that actually reacted. So we got less than that in terms of the overall enthalpy. So what do each one of these symbols mean? Well, this one here is talking about the molar enthalpy of combustion. Right, where the C is standing for combustion, M is standing for molar. Okay, and the next one is just getting you the enthalpy of formation. The little f stands for formation. However, this is for the total formation. This one here is just enthalpy of reaction. And this is just the total reaction that took place, not per mole of any particular substance, but the whole reaction. Whereas this last one will get you the molar enthalpy of reaction. That is the amount of energy per mole of a substance. Let's take a look at one last thing here. Propane. The molar heat of combustion of propane is 2043.9 kilojoules per mole, which means that for every mole of propane that is burned, we're going to get 2043.9 kilojoules of energy. But we are only burning 25 grams of propane. Propane, if you remember, is C3H8, which, taking the 3 carbons and 8 hydrogens, 12.01 times 3, means that this will have a molar mass of 44.11 grams per mole. Right, so to find the number of moles, that's mass over molar mass. We're taking the 25 grams divided by the 44.11, which means the number of moles is 0.566 moles. Lastly, we just want to figure out how much actual energy, how much heat is being released. Q is equal to NH. Well, we know the H value here, and we know the number of moles. And so this is just going to multiply 0.566, multiplying that by the 2043.9 kilojoules. And so finalizing this off, you're going to multiply by 2043.9. That means 1,158.4 kilojoules of energy are released.